Welcome back. Thank you very much for, again, taking your time to stay back. Promise you to be equally exciting this next half, where we will perhaps dive into even more discussion about the importance of integrating architectural design with engineering and many of the technical solutions. Because as I was talking to some colleagues outside, ultimately, the stakeholders will become more comfortable and more convinced when the disciplines come together and present a united solution or united front, as opposed to the traditional where the architect does something and then the engineer say, no, this cannot be done, that cannot be done, and the client is left in the air. What should we do? I think the collaborative and truly integrated approach is going to be key to address our carbon and all the other issues moving forward. So with that, let me introduce a first friend and colleague who have been partnering us in the journey in this search for a long, long time, Wolfgang Kissling. He's the director of Transsolar Energy Technique from Germany in Munich. International work, have worked all over the world, in Singapore, the region, and so on. He has managed many, many high-profile projects, and you can read, actually it's quite well published too. You can read many of these projects on in different sort of media. And important thing is to celebrate, again, this point about architecture, quality, as well as the whole adaptive comfort, focusing on practical solutions, and always about human-centric, delivering human-centric performance. So with that, okay, over to you. Thank you.
Lam Kipo, thank you very much. I apologize a little bit for my voice today. I want to say it's a huge honor for me to have been part of your journey of NUS in the last many years, I need to say, starting and working on the School of Design #4, continuing with your team in the project of School of Design #1 and 3. So it's a big honor for me to speak today. And I choose the perspective of, let me say, a professional climate engineer to lay down some arguments, but also of a very personal view of that project. And when I was asked by Nirmal, at that time Vice Dean for Special Projects, and by the team of Eric, would you have a look at our School of Design 1 and 3 building and let us know what you think? Actually, for me, this journey started not with carbon. This journey started not with embodied carbon or energy efficiency or reducing carbon in operation or whatever techniques or technologies. It basically started with exploring a tropical building, and that's what I found is a hidden treasure. So what we found in this building, what we saw in this building basically was a huge opportunity envisioning ourselves into the changes which are required to create a building which is comfortable, which is inspiring, where I would like to work, where I would like to teach, where I could imagine my children to study. That was the idea. That was the idea, to think about how could the facade look like? How could the facade, instead being a barrier between a carport and a building which is completely sealed, become something which is blending between inside and outside, pulling people in, getting people into the building and become a nice entrance. That was the vision. We started with the vision for the people. And what we found, we have seen that several times, it's so obvious that that building needed a change, because yes, there was no daylight, there was no view to outside. Even the fresh air you cannot call fresh air. It was bad fresh air, low comfort, no quality. So that was basically what we found, but we saw actually there is more opportunity. Just one more slide for the facade. The facade was just designed to block off tropical sky, but basically ended up to block all daylight. So with this starting point, we have been thinking, and we have been trying to support the design team around Eric with communicating ideas, potentials. We have been communicating what do we see. And I remember myself that I was walking with Eric through the building, standing up on a chair, trying to open the false ceiling, taking the flashlight of my camera, flashing into the false ceiling, and I just received a black image. Nothing. This was a huge volume, black and blinding out. So even on my flashlight, I couldn't see anything. So we figured out there needs to be something. There is something. There is space, and you will never get this space back into a building when you just go with economic thinking. You will never get the kind of spatial quality back. So the ideas, what we communicated to the design team was like more ideas, throwing in with our eyes as professional climate engineers, what we would do, open the facades, cut in an atrium, just connect the floors, open the other side of the building, connect from the north to the south, just connect across from east to the west, just connect across the site for natural ventilation, so do crazy things. And we offered actually analysis like this, where we all, here you see what has been hidden in this diagram. So we offered diagrams where we always looked onto what is how we see the existing, and just have a look and keep your eye on the word existing and what is the potential. If you really get all the false ceiling out, this is the potential what we saw. We never made these inputs to Eric and to NUS as design decisions. It was more food for thought. It was like, we see this potential, take it serious, don't let a physicist as myself design something. Take it with your professional qualities as an architect and take it further into design. Again, we showed this is the existing quality at the moment for daylight, and we could imagine that it becomes a way more daylight autonomous building with a higher daylight autonomy. Similar things for the thermal zoning, for the natural ventilation. Because of no daylight, no natural ventilation, because of the closed facade, it was a completely air-conditioned, sealed building at that time. And we suggested, let's be crazy, just make 2/3 naturally ventilated. I'm completely aware of the limitation of naturally ventilation in your climate, but we suggested this to have a strong voice for changing something, for making the facade and the building as an entity operational for people. Thinking about hybrid comfort, thinking about a different zoning which allows to think completely different how such a building could work. This is a typical section which shows elements, what we evaluated in that early schematic design change, to verify this is not just dreaming, it would work. This kind of building would work, and that's what we then again sent back, exchanged with the design team of Eric to say, trust, it works. We can have the facade upgraded, the windows upgraded, we can have daylight. Your external shading system, which was nicely designed and taken over by Eric, works. It brings daylight into the place, and you see it in the next slide, how it's implemented. You have seen these slides before, so somehow you see brotherhood in mind between architecture and physicist and climate engineer. We have not been talking about what we are going to show. Just see the white ceiling to make it better bouncing back, and I will finish this part of my presentation. I was visiting the space with Eric a few months ago, and I was specifically looking for that position in the studio where this famous quote was taken, and it looks like this. Let me zoom out from here and talk a little bit about low carbon design. Basically, what we typically do when we start working on projects, we try to create a vision with the design team and with the client, laying down 3 basic steps. Reducing carbon emissions in the construction, in the embodied carbon, reducing carbon in the operation, and replacing all the energy with renewable energy. This 3-step, kind of simplistic, is a super strong story to help everybody along the design process to keep track what we are doing. Typically, and professionally speaking, that's done with a life cycle assessment, and there are the different phases on this on the screen. What my company does, Transolar, since 30 years, is typically focused on a sub-phase, which is B6, operational carbon because of energy use. What we did for this project, we have been looking for cradle-to-gate carbon numbers in the construction, and we added the reuse or the omitted carbon emissions because of the adaptive reuse of the buildings. And we went through that process by, many of you who have been working with me know that we have been instrumental to implement the hybrid cooling system in the School of Design number 4. I will not talk about, just show one slide. It is the idea of making comfort in a different way, which is similar comfortable, but doing that with less technology and less energy. Back to carbon in the structure. Reducing carbon in construction. What we took at that time was the 3D model we could receive from Eric's team. We broke the entire building down into major parts which are retained: foundations, the walls, columns, the floor and the roof, beams and stairs, and building parts which have been refurbished, like ceiling and floors, windows and shading. And we estimated the masses and the construction types of this, and we took images like this, and I've been talking with a structural engineer to help me. How much steel could that have been? What kind of cement was that? Is that a concrete 25, 35, whatever, to get a good idea of what kind of materials have been used. This is one part. You need the material and the masses, but then you need to think about what are the specific emission factors. And at that time when we did that in 2019, 2020, it sounds ridiculous, we couldn't find these numbers for Singapore. There was no database existing. So I said, oh, no worries. We have in Germany, we have a good database, Ökobaudat, since 20 years. So let's just build that building in Germany using the German numbers. And the German numbers are the red, in the range of the red dots. And we figured out, oh, let's be careful, do the same thing for the UK numbers, ICE numbers, inventory of carbon and energy, using international numbers which are published in the UK. And then in a third step, we went through some scientific papers and publications in Singapore to figure out what are the local cement and the local concrete values for carbon emissions, in the absence of having better numbers. So we had a kind of lower, a mid, and an upper range. And I apologize for this complicated diagram. And then based on the masses, based on these different carbon emission factors, we developed 3 scenarios from the top, using, if this building would have been built using the carbon emission factors to our knowledge in Singapore, roughly we estimated something like 500 plus kilogram CO2 emissions per square meter of floor, roughly. We figured out that the ICE would be in the middle, 400 plus, and probably the German, if that building would have been built in Germany, would be in the range of 250. And taking that thinking further, if we don't build that building, if we reuse that building, we probably save the emissions which are related to the base building. And that is the second line from the bottom, which shows if I save these emissions because I retain the building and I have only the changes and the emissions of the changed materials, then we are probably roughly in the range below 100. Don't take the numbers too serious. There's probably changes and we miss something. But in this range, if I always take the same kind of methodology, that would be the reduction. So probably we drop down from 500 to something to 100, probably. And the last is what Eric was talking about. We imagined at that time a reuse of all the shading and aluminium in the facade, which we couldn't get through the design process, but that would be the last option down there. Cross-checking if these numbers make sense. Sorry, before I do that, let me set carbon emissions in construction in context and in perspective to carbon emissions in operation. That's done in this kind of carbon story here. I just use it for setting that context. These are numbers, take care, absolute kilogram per square meters and 30 years. The golden and the brown is the embodied carbon, and you see in the first step how the embodied carbon is reduced because of the retainment of the original building. And we just had that comment before how important operational carbon and operational emissions in Singapore are from Ken Young from BCA, and you see the huge blue bar dropping down to the super energy efficient system in operation by changing the way how the building is operated. And then it goes on with the green bars to show how much of this energy could be produced on the roof and how much could that be produced in the microgrid. That was our conservative estimation 2019-2020. Just this morning we learned that you are on net zero for one of the buildings. So we have been super conservative. Basically that means that you already go from here to here without using grid or energy which you borrow from your neighbor. I understand that you net zero in the definition that you use the energy produced on the roof goes into your building. But it shows a kind of perspective, setting these different carbon contributors in perspective, and basically shows operational carbon is still a big animal and big elephant in the room in Singapore. Let me go back to the embodied carbon. The lower, the middle, and the upper range, and compare these red, green, yellow to numbers or to a statistic what we find out of the UK. And it made sense for an educational building that they somehow, with the different use of carbon databases, somehow mimic the range of existing buildings in statistics. So we felt quite good. But when I was looking on the then, a year later, published data from BCA, I was surprised to see that BCA has numbers for non-residential in the range of 1,000, 1,500 for residential, and 2,500 kilogram per square meter carbon emissions, which is quite high. And being a scientist, I think this is something where I suggest that universities, that NUS, dig deeper, make a deep dive. Where is that coming from? As much as I trust that we have found the kind of yellow, green, red range, if that building would have been built according European standards, I think there needs to be some truth in these super high numbers for embodied carbon in Singapore. And I can imagine that by the different bylaws which exist in Europe, which force our construction industry to be very material and resource efficient, as a byproduct, we already use less material and have less embodied carbon. I think that's something which really I suggest to be a research topic in the next years for the NUS to figure out where's the difference coming from. I've been visiting buildings here, high-rise building with transfer slabs of 7 meter high, things which are not existing in Europe. I would not be aware of a building, you probably, Hussein, but I would not be aware of a building where I find transfer slabs of that massive material, steel and concrete use. So I suggest to figure out where's that coming from to bring both worlds somehow together, because we need to explore the low-hanging fruits. And if this would be that the construction can be smarter using less material, that would be my first choice to do. Because this is something which can be solved with intelligence and with money. Okay, 3 more slides. I zoom out. What really matters are low carbon projects. This is an example what I've had the privilege to work with in Sydney at Lazy and High Rise building. And what you see is a building, and you see it a little bit, it's stacked out of habitats of 4 plates. And these habitats basically are concrete steel slabs on which a 4-level completely wood building is sitting, and then again another concrete steel slab and another wood building. This is to bring both worlds together. You can do that out of concrete, but you can put in wooden structures into this and use the benefit of structural of the strength of the steel and the concrete for the structural stiffness, and put in the wooden structure. Why would you do that? Because industry and building industry, and that probably sounds ridiculous to you, has a possibility in the next 30 years to contribute through absorbing biogenic carbon into our buildings to buy us time. By getting wood, CLT, mass mass timber into the buildings, and keeping it safe in a building, we reduce and we bring carbon and biogenic carbon out of the atmosphere into a kind of storage process. And we are going to build a lot on this planet. So there is a kind of inherent storage possibility in the design of buildings if we would like to explore that. There's a simple, super simplistic, but probably interesting cycle to see. When 1,000 kg of carbon are absorbed in 1 cubic meter, roughly 700, or roughly, and that's the rule of thumb which I often use, 180 kilogram per square meter of floor plate are negatively absorbed and compensate for roughly the same number of a concrete floor. Rough numbers, context matters, but I think it's not off, it's in the same range. So it makes sense to think in this cycle. And that cycle matters because as much as we like to and need to work on reduction of emissions, at the end, we still have emissions. It's still more carbon in the atmosphere as before. And the only mechanism which exists are nature and bio-driven mechanisms. Trees and our oceans, which absorb carbon out of the atmosphere. And we need to absorb carbon in a range, and that's a number I learned on the 80th Forum for Life Cycle Analysis in Switzerland. We need to absorb carbon and store carbon if we want to make a benefit to the climate for 300 generations. 100 generations to 300 generations. That's something like 3,000 to 8,000 years. And when I heard these numbers, oops, hard to imagine. What I can imagine is that we buy us time for 30 years to think, what the heck are we doing? Thank you very much.
Thank you, Wolfgang, for that. A lot of numbers to digest, but it's important to quantify. When you talk about, sequestering carbon, I was thinking of his keeping the soot in the chimney. That kept the carbon there. Right, so moving on. Next speaker is Nirmal, no stranger to many of us. Nirmal is associate professor in the Department of Architecture. He's spent his whole life on sustainability as a strategist, author, educator, and very passionate advocate all the time. He was a vice dean with me for a little while. Then he came and said, I'm really tired. After having seen through SD4, I completely sympathized and I said, okay, I'll let you go. And then Eric stepped in and continued that process, of course, in a very seamless way. So without further ado, I'll just leave it to him. He's, by the way, also our alum, so very proud as well.
Thank you, Kipo. Thanks very much. I shouldn't say, but these projects are very tiring, exhausting, if you don't have a mental breakdown first. Anyway, I'm going to talk about something completely different. I'm going to report about the work that's being done in the postgraduate program that I'm a co-PD of, the MSc Integrated Sustainable Design. The other co-PD is Wong Man Sam from WOHA. He teaches with me. And last semester, we decided to introduce a simplified carbon calculator into Studio. This was done, of course, with the help of our old friend Wolfgang Kessling, who came last year to run a workshop, and also inputs from Gregis Ryman from Malaysia. So now, for those of you who may not be familiar, teaching in design studios is something quite specific. It's problem solving at the drawing board. It's scenario-based learning. It's highly speculative. Very often it's conceptual and strategic in thinking. So what I'm about to flash are works of students. Please forgive the naivete of their drawings. It's done in 10 weeks. It's a real rush job. The purpose of the studio was really for them to come to grips with the idea of carbon using this calculator. Yeah. Now, carbon in the teaching of design is very challenging. Why? Well, as you heard from Wolfgang, it's complicated. It is complicated. And if you're going to do it in a design studio for in a very rapid amount of time, then it proves very challenging. I mean, every piece of a building has a carbon impact. Every piece of what you put in there comes from somewhere. And then you've got the longer issue of operational carbon and energy and where that energy comes from. Most students aren't able to process all of that. Now, I'm going to show you the BCA carbon calculator, which attempts to reduce the granularity of the problem into a spreadsheet. So this is the BCA carbon tool, which requires inputs on quantities of each material, the place of origin, the choice of transportation, etc. Yeah. I mean, this is clearly the type of tool that is very useful in what I call downstream thinking. It's a kind of an accounting tool. Once you've made the design decisions, great, it'll tell you where you are. But how do you begin, right? Where does carbon begin to shape upstream thinking as opposed to the downstream accounting? In design, we often start with very strategic decisions about the form of the building, and this is central to what we do in the training of architects, where we talk about situation and purpose. And many of these early decisions have a very profound impact on the life of the building, both in terms of its energy use and its adaptability. In the program that I co-direct with Mansam, we have what's known as a systems approach to design. And here we introduce an additional layer of thinking into the design process, which is to say that we ask our students to not just demonstrate how their buildings consume less, but how do they then go on to produce energy, water, food, accommodate biodiversity, public space, mobility systems within the design that they're proposing. So they have to bring into this conversation these additional systemic layers. So before I talk about how carbon feeds into it and what the carbon calculator does, I just want to show you an example of one student's work from an earlier semester. This was the work of Nopur Joshi. Typically what we do is we start the studio off by giving students projects, buildings in Singapore, and we say, now go redesign it, reimagine what this would look like if you were to bring systems thinking to the table. So she picked, rather bravely, I think, the Singapore Parliament project. The upstream question, of course, had to address situation and purpose. They're not excused at any point from dealing with architecture as architecture. Yeah, just because you're dealing with systemic layers doesn't mean that you have to forgo functionality or amenity or basic design logic, and it's got to look good as well. I mean, as an idea, it's got to have something going for it. But onto that, we then asked them to demonstrate how the project integrates layers. Here is, for example, the integration of water as a system. Here is how energy was introduced into the system. So they actually have to not think about these things in sequence, but simultaneously. I'm oversimplifying it a little bit by showing you these images as a sequence of events, but really it's a battle. So much of it is about unlearning how they've been taught to think about design and to bring additional layers of thought into it. It becomes a battle on how to bring additional thought processes into the way you do good design. Yeah. What's interesting then is that when we step away from the work of many semesters, and we've been doing this form follows system studio for quite a while, we begin to notice that there are a few key defining aspects that at this stage of thinking, this conceptual stage of thinking, students are grappling with. One is the boundary conditions of porosity, the envelope, space and structure. Yeah. How does this relate to carbon? Well, that's interesting because here is the SDE4 building, the images that were published by Seri Multiply at the beginning of the process. And there is a parallel to what the students do in that the very early conceptual thinking about the form of the building begins to look at porosity, begins to look at surface areas, begins to examine the relationship of the building to the climate. And the things that come out of this that have an impact on the performance of the building, these ideas, they shape energy demand, they shape capacity for online power production, and they offer the potential to shape materiality. And these, in the context of what Wolfgang was saying about what shapes carbon affects both operational and embodied carbon. So if you can make the right decisions at the beginning about porosity, about boundary conditions, about materiality, tectonics, you potentially have the possibility of impacting the life cycle carbon of that project. So how do they do that? Well, this is where Alakesh, my co-author, came up with this simplified carbon tool. It's for architects who go a little cross-eyed if they see too many numbers to graphs. This was the perfect solution, which is to say, you've got a design, put in the numbers, and the tool will spit out the outcome. How does it work? Well, on operational carbon, there are benchmarks describing what a typical building in Singapore consumes. We had ideas of what the overall efficiency of the systems could be improved, by how much. And this had a lot to do with benchmarking high-performance buildings in Singapore. And then to that, all they needed to do was enter the areas for space cooling and non-space cooling, and that would give them, in a very simplified way, the energy demand, a guesstimate, if you will, yeah, of how that building is doing. The question of energy production had to do with the envelope. The roof had a certain yield potential, facades a different yield potential. And the total energy demand would be, the total operational carbon emissions would be the total energy demand minus the total energy generated multiplied by the grid emissions factor. And the grid emissions factor is basically describing how much carbon is embedded in the electrical power that we get, depending on what the source of fuel is. So in our case, natural gas. And so the number for Singapore is 0.48. All of this is pre-programmed. Don't need to think. You just plunk in your surface areas and it spits out the answer. Embodied carbon, we simplified it, dumbed it down a little bit to give them various options of structural systems. So the first option was, and these figures on the intensity of embodied carbon for different structural systems for different types of buildings came from literature, meaning these are published data, not for Singapore. And so this is obviously a room for research. We should do that, but also with inputs from Wolfgang and Gregors. And then students were given a choice of either having full RC steel with CLT or CLT with full timber. And so they had to, again, they could make hybrid buildings, they could make composite buildings made up of a mix of these things, and they would then key in the numbers. Again, the no-brainer approach, enter the surface area of each option, and the calculator would do the rest. Of course, we held students accountable to basic principles of passive design and structural logic. So if you're going to make a fully timber building, you can't have these massive, heavy loading, wide span structures. So there were certain constraints, rules of thumb put into the process that they had to abide by. Okay, so this is what the output of that calculator looks like. You get a number for embodied carbon, which is usually the new construction, or depending on whether it's new or retrofit. And then you get a 50-year step cycle for operational carbon. So how much does it consume cumulative over a period of 50 years? Time is very important in this conversation on carbon. It's not just what happens on the day of completion. It's what happens over the life of the building. So the longer the building survives, the greater the operational component, the less the embodied energy component. This is an interesting dynamic which we have to come to terms with. Yeah, the shorter the life of the building, the greater the embodied, and the lesser the operational. Anyway, there was also some provision for minor and major retrofits every 10 years. So I'll show you very quickly the outcome of this studio with the work of one group, one pair of students. They were given this complex in West Jurong, the Westgate Mall gem with the Jurong MRT station and the bus interchange, and they were asked to redesign it, right? And they had to either retrofit it or completely redesign it. Now, the calculator allows for certain conditions of retrofit. In a retrofit situation, you don't get the same performance as you would with a brand new design. From an energy standpoint, that is a given, right? It does better from an embodied point of view because you've got that material base in there, but from an operational standpoint, usually the performance metrics are not as high. So this is what they came up with for the retrofit. I'm gonna flash through the images because they're mostly just illustrating the outcome. They opened up some of the floor plates to create more natural ventilation, reduce the demand for energy, etc. And couldn't do much with the material. The RC building, well, I mean, you want to keep it. That's the whole point of a retrofit. But because so much GFA was lost, they had to add some floor space with CLT, lightweight timber construction on top to offset some of the losses. Okay. The envelope surfaces for solar, not a very high self-sufficiency rate. And this is what that retrofit scheme kind of looks like. Yeah. And then the second part of the task was to redesign it. So we were, and I should add this, that studio is part teaching, but part learning, and we're learning as well, you know, the tutors. We want to know whether it's better to retrofit or redesign, tear it down and redesign. That was a question. I'm not sure that it's answered in one semester, but it was a question that we were asking. And so ISD studios tend to be kind of de facto research processes, yeah? So they came up with a high-rise option where there were 2 towers and a podium with much more solar PV greenery that the retrofit would have allowed. And they came up with a low-rise or medium-rise 8-story with a much flatter roof that you could maximize the potential for solar and so on. And this just shows you what the high-rise and the low-rise options look like with the thermal zoning, the air-conditioned and the non-air-conditioned spaces. These are the numbers for how much envelope, how much solar PV, how much energy is produced. Predictably, the low-rise option does better. Yeah. This shows you what the materiality and the structure. Again, predictably, the low-rise option does better because then you have the option to use wood in a more extensive way. And these were the results where we put the numbers in. So the line on the very top shows you what the building would have done had you not done anything. And the 3 lines below that show you the retrofit, redesign high-rise, and redesign low-rise option over the course of 50 years. Yeah, how that plays out. Now, some of the interesting things that popped up were that actually the redesigned building overtakes the retrofit building in terms of a 50-year life carbon usage. And that's because the calculator operates on an assumption that with a redesigned building, you can have much deeper gains for operational energy. Keep in mind that for a 50-year life of a building, the operational energy is about 80% of total carbon emissions. So it's weighted depending on the time. If you had narrowed that window to 40 years or 30 years, the numbers would have been different. Yeah, but there is a point of parity at which the retrofit and the redesign cross each other with this calculator. And this kind of shows you. We saw this consistently in and I should add, it's a sample size of 5, so not quite research worthy yet, but in all 5 schemes, the redesign scheme did better over the 50 years than the retrofitted scheme, notwithstanding the embodied energy. That's a question. It's not a solution. I'm not saying that you should automatically tear down and build again, and there are many reasons for keeping buildings, but I think there needs to be a lot more research done into at what point how does this play out over time, right? The other question that we were asking is what this meant for high-rise and low-rise buildings. Again, it's very clear that the high-rise building doesn't do as well as the low-rise for obvious reasons, the potential for solar on-site generation. But, it's not just about carbon, right? It's about other systems as well. And the high-rise option gives you other privileges. It allows you to use the ground in different ways that a low-rise option may not. So you kind of weigh out these discussions as you go along. This is not the graph doesn't tell you exactly what you have to do, but it gives you the relative position of the various options. Whoops, sorry, too quick. And finally, the question that we were asking was, is there anything that becomes carbon negative? Is there any? And it had to do with program residential developments over time, especially if you go for redesigned low-rise, can actually begin to extract carbon out of the system, meaning they are producing more energy than they need and therefore offset carbon, right? So again, the studio was the beginning of research, and these are the questions that emerged from the studio that I think Mansa, myself, and Alakesh, we're going to keep poking at and see where we go with this. And the other thing that we want to do this semester is to examine what this means at the urban scale. How do we aggregate buildings and create a carbon story in neighborhoods and so on? That's it. Thank you.
The profile of students in the program. How many are architectural? How many are engineering over the years?
Right. So we have, the question is how many architects and non-architects do we have in the program? We're still a bit weighted towards architects, meaning about 60 to 70% architects, but then we have about a third to 40% who are not, who come from different disciplines, engineering, environmental science, landscape, so on.
Well, thank you, Namal. That's clearly a good start in this push towards cross-disciplinary approach to solving integrated issues and complex issues like that. I'm particularly happy, like just now a question from the student from biological science and many other disciplines. The next speaker is Associate Professor Kwa Han Wei. I have to tell this story, Han Wei, because Han Wei is an alum, but not from our school. He did his master's degree at NUS as a research master in theoretical physics in 1999. And then he came to see me. I was the dean then. He said, Prof, I really want to apply my knowledge in the built environment. Is it possible? I said, of course it's possible. I said. And that journey began in his career. By the way, I had to convince the university admin to allow me to hire him. The first question the provost said, why are you hiring a physics person? You're architecture, nothing to do with you. I'm not making this up. And after that, when he said, I want to go and do a PhD, I had to defend that. I had to see the provost 3 times before the provost approved him. By that time, I was the head of Department of Building, and he was my staff. Started from there in 2000. Long story short, he went to MIT, did extremely well, came back, and now he's one of our really, really important anchor staff in the college as well as in the Department of the Built Environment, which is what it's called now. He's now Vice Dean of the Alumni Relations. He's great with students. He has lots of ideas with the students to motivate them to do all kinds of things, which is great. And his work on biochar has been internationally known now, and has won many, many awards. So without further ado, Han Wei, over to you.
Thank you very much, Prof. Lam. Well, a little bit more about the story behind me joining the built environment. The problem with the leaders back then in approving my hiring is that, well, I spent many years studying structure. Not the structure of building, but the structure in protons and neutrons. So they were wondering, what is this guy going to do in building? But anyways, thank you very much, Prof. Lam, for bringing me into this circle. And I'd like to take this opportunity to really say a big thank you to Prof. Lam. Maybe he's too modest, humble to mention this. He's actually one of the major forces behind SDE 1, 3, and 4. we all know how difficult it was, right? We were working on how to prevent the, well, yeah. And well, thank you very much. And today I'm going to talk about something rather different, all right, from the materials and engineering aspect. And I promise you I won't be talking about the structures of protons and neutrons, all right? From net zero energy to carbon neutrality, what does it actually take from the materials aspect, from the system perspective? All right, this is my outline, and I'm going to start with some basic definition so that we are all on the same page about what we mean by carbon neutral before I go on to something which I've been working on for the past 7 years or so, and that is biochar. Net zero. And I think by now, when it comes to net zero energy, right, we know that it is about balancing what we need and what we produce on site. However, we all know that in the classical definition of net energy, all right, we might not have considered life cycle or embodied energy. Let's talk about energy first before we deep dive into carbon. So for that, we need life cycle assessment. It's great that we have already talked about life cycle assessment, Wolfgang and of course Nema. So over here, I'm just going to very briefly and quickly run through the whole idea of life cycle. As you can see here, these are the different life cycle stages of a material. Let's say building material, any material, steel, cement, and so on. So in life cycle assessment, basically what we are doing is that for each and every one of these stages, we account for the input and the output. And when we want to zoom in onto carbon, it will be about the carbon emission due to this input and output. We do this for each and every one of these stages. Sum them up. This is how we account for life cycle carbon. Very simple concept, very easy for me to talk about, but extremely hard to do it and to do it well, just like life. Talking is simple, doing it well, difficult. So how about carbon neutrality? All right. And what's the relationship between being carbon neutral and net zero carbon? So to explain that, I would like to depend on a picture contributed by Shoka in 2020. So over here, you see that at the top line, and focusing on concrete. Let's talk about concrete because of the somehow and somewhat notorious emission profile of cement. You find that in concrete, let's talk about cement first, right? The carbon emission can come from two places. Emission due to fuel, fossil fuel, that's it. And of course, in a calcination of limestone, right, to give us the clinker, and then with that, cement. So the whole concept about being carbon neutral is that I've got to do something here in order to offset. And that alone, that piece alone, at least in magnitude, must be the same as whatever I have put out in the atmosphere. How can I do it? Carbon offset. All right? Carbon capture and carbon sink, which are some of the ideas that I'm going to share with you very briefly about. And what if we are able to take the next step, all right, which is here? I'm going to switch to clean energy, and technically speaking, that will allow me to hopefully reduce or even eradicate the CO2 emission from there. But still, I have one little piece here, which I'm going to offset with whatever I have, including carbon capture and sequestration. And what happens if I can do even better? I'm right here. All right, there's no more emission, technically speaking, and therefore there's no need for me to offset anymore. So as you can see here, in order for me to reach net carbon zero, I need to start somewhere, and that is to ensure that in every single step, I go for carbon neutrality. So for the rest of my talk this afternoon, it's going to be maybe 10 minutes more, I'm going to highlight some of the technical challenges in meeting that very target. All right, so these are 2 points which I would like to emphasize, and I think it's great that you guys have already talked about the importance of having life cycle carbon assessment. Moving on, carbon negativity. All right, Namal, good. We didn't really pakat to talk about this, right? All right, carbon negativity. You have heard some people talk about it. At the material level, is it even possible? Well, it depends on how you define carbon negativity. Let me share something with you. And that is something that I have to talk about, and that is biochar. Traditionally, biochar has never been talked about within the construction material realm. All right, so what is biochar? Self-explanatory. It is a byproduct of a process which is already well studied, well understood. And by that, I mean pyrolysis. Okay, pyrolysis is about heating biomass under a very controlled environment. And then, in order for us to fully understand and appreciate why this can be carbon negative, we have to be mindful about a few things. Number one, biochar is just one of the many byproducts of pyrolysis. We still have synthetic gas over here, and of course, bio-oil. Okay? So what we are going to do is to make use of the synthetic gas to replace an equivalent amount of fossil fuel, and that will give us the carbon reduction. And in fact, I'm very happy to share with you here that a group in Cornell, my colleagues in Cornell, actually came out with an LCA focusing on biochar made from different feedstock, which are shown right here, first column. And they show that in many of these options, carbon negativity may actually be possible. Let us zoom in on the first row. All right. So what they found is that if you take into consideration emission and reduction, the net is a negative value. So now let us deep dive into these two aspects of carbon reduction. The dark blue, stable C, stable carbon. So the whole story about biochar is that when you turn biomass into biochar, you stabilize the carbon and you prevent the carbon from being lost in the form of CO2, carbon dioxide. Besides that, there is an avoidance component. By using the synthetic gas to replace fossil fuel, you avoid having to emit CO2 due to the usage of that equivalent amount of fossil fuel. So, and there is more. So at this point, I would like to switch gear to talk about biochar concrete. It is a carbon-based discussion. You are not going to see equations coming out over here. There are altogether 6 ways by which biochar concrete can contribute to a net reduction in carbon. However, I would like to mention something. Even if biochar is carbon negative, it doesn't mean that if I use biochar and I put biochar into concrete, that concrete is going to be carbon negative. It doesn't work that way. All right? It doesn't work that way. But at least, as you will see in a while, it can contribute to reducing the overall carbon emission of concrete. Starting from point number 1, the C, the carbon C, or rather the stable C that's locked in the concrete. Secondly, like what I've mentioned just now, the avoidance. Avoidance can be in the form of CO2 emission reduction due to the amount of cement that is saved or avoided. Incineration of wood waste in an incineration plant. If we divert the waste stream to concrete, we avoid having to direct those into incineration. And of course, the diversion of fossil fuel or the avoidance of fossil fuel and the emission due to that. Next, number 3, very interesting. In case we have the option, we can also consider carbon reduction due to carbon capture and sequestration. All right, out of our control because it really depends on the location. Next point is interesting. It is a rather new concept called ACC, accelerated carbonation curing. I've been working on this, one of my papers, hopefully is going to get published. And this is the whole concept. I think a few of our friends from civil engineering might have heard of this as well. So carbonation, as we all know, is a process that happens in nature. Okay, it is about the mineralization or the conversion of CO2 into carbonates in concrete or in cement. All right. In the case of ACC, basically what we are trying to do is to speed up the process by exposing, curing mortar or concrete, okay, in an environment of very high CO2 concentration. And that is to basically use it as a pump or as a sponge to absorb as much CO2 as possible. All right, there's a limit though, and I'm going to talk very quickly, briefly about that. So these are the substances, materials within cement that got converted into carbonates. And I would like to draw your attention to this particular guy, CSH, calcium silicate hydrate, that awesome material that holds the particles together in concrete and therefore making it strong. Anytime you have any one of these guys being converted into carbonate, there will be a weakening effect, which means that the concrete is going to be weaker. But at the same time, of course, when you have calcium carbonate being very fine particles, reducing the overall permeability of concrete, it will help to bring up the strength as well. So there's a plus and a minus. It is all about, well, as in Mother Nature, it's all about balance. And therefore, the net strength can go either way when you use ACC on concrete. So coming back, the fourth point is this, and I get this question almost every time I speak. The question is this, all right, you keep saying that biochar can strengthen concrete, and it's true. I mean, it's not just my team. Many teams around the world have proven that if you add a sufficient amount of biochar, as shown over here, okay, in these two clusters, we make use of different kinds of biochar from wood waste and food waste, all right? And you notice that the second bar is always higher, and that includes 1% by weights of biochar. So the question is this, since you have shown that by adding some biochar into concrete, we can actually, well, reduce the size of the component, right? The concrete component. Well, I'm not sure. Perhaps it is possible. I've not done that kind of research yet, but if we can do that, then that will help to reduce the carbon as well. So one area for you to think about, and maybe even join me in the future for further research. 5 and 6, we can also reduce carbon emission from concrete by resorting to recycled aggregates, and of course, pozzolanic replacement. Pozzolanic means cement-like. And most of the time, we make use of different waste-based material to at least partially replace cement in concrete. Take a step back, we have altogether 6 different ways by which we can reduce carbon emission in concrete. So, I think many of you will have this question in mind. If we are going to put all these 7 factors together, how is our concrete performing now when it comes to net carbon emission? Are we neutral yet? We are far from that, all right? So I'm going to share with you, right after this, some of the cases that I've worked on. But anyway, this is just a pictorial representation of the kind of materials that we have tried. We have looked at, not in my lab, but as an industry, to hopefully green concrete. Okay, this guy might stand out, food waste. If you want to make use of food waste in building materials, I think the only way is to convert that into biochar. And I think the motivation is out here. Right now, after a few years, we are still at 19, 18%. We can do better. Perhaps biochar is the way to go. All right. So now, I'm going to spend the next 2 minutes on this, or maybe a bit more, 4 minutes. Base case, what happens if I'm going to put 2% by the weights of cement in the form of biochar into concrete? And at the same time, all right, I'm going to continue using the synthetic gas to replace fossil fuel. I'm not going to do carbon capture because maybe I don't have an option. For example, in Singapore, ACC, right there, 2 millimole of CO2 per gram of biochar. Now, this is a very optimistic figure, all right? Experimental base, I've just completed a review on this. I'm just going to put it out there, okay, 2 millimole. Okay, we'll see how it can be increased in the future. And the rest, I'm not going to change. The result, I only reduce the CO2 emission of concrete by 6%. Better than none, but not good enough. So let us get a little bit bold, right? I call it the case study of C-neutral bold. So how bold can I get? Right here. I'm going to make use of 5%. Put in 5% by way of cement in the form of biochar, and at the same time, take away an equivalent amount, mass of cement. Problem. Technical challenges, number one. Anytime you increase by too much, you reduce the strength of concrete. However, I think we have not found a way, and there is a way out there, where we can continue to increase the amount of biochar without reducing the strength of concrete. Secondly, CCS capacity. In this case study, okay, I'm imposing on myself to have at least a 0.4 kg CO2 equivalent per kilogram of cement produced in a plant to be removed using carbon sequestration. Is it possible? It depends. It depends on your location. Optimistic, I'm going to have an ACC of 3. And of course, in order to do that, I need to increase the dosage of CO2 into the cement or into the concrete. The challenge is that anytime I do that, there's a chance for me to reduce the strength of concrete again. So we have a lot of problems, right? And in fact, if I go down, you'll find that the challenges are there, but at least it becomes clear and we know what are the targets to hit. Right now, if we are going to use RCA, recycled concrete aggregate, and we are going to use GGBS, we are able to reduce CO2, if I'm being optimistic here, about 30 to 40% respectively. So if I'm going to set a target as 40 and 50 here, I'm basically asking myself to do a bit more in order to push them up by 10%. It's not easy, but it's not impossible. And that, if I put together, will help me to achieve carbon neutral concrete. Okay, very optimistic, I know. I guess that's what set us apart. I mean, we are here because we believe that we can change the world. Last but not the least, I can also see how I can make use of the bio oil to replace an equivalent amount of fossil. Still a very new area of research. If you're interested, come talk to me. I can point you in the right direction. That's it. But how about this? All right, Joe, how about this? I'm going to also aim for 100% carbon neutrality, but I'm going to be conservative by sticking to these numbers. I'm not going to change the size of the concrete component. I'm going to stay at 30, which is our best case now, 40%, okay, reduction due to the use of greener aggregates and greener option of cement. But guess what I have to do? Right up there. I have to increase my dosage of biochar to 28%. Now, this is a situation we are facing now. To increase to 2 to 5%, we are facing a problem. How optimistic, how possible are we to increase all the way to 28%? I'm not a person who says that it's impossible, all right? But I think in order for us to make use of this ultra-high biochar content concrete, we really need a breakthrough in ideas. I've got some ideas, but I'm not sure yet. So this is what has been keeping me awake for the past few months, thinking of how I can jack up the numbers when it comes to biochar dosage in concrete. And of course, in a possible future, when it becomes possible for us to hit this 28% target, we need to make sure that the economics work. It's no longer just a technical issue, but about cost, about policy as well. In conclusion, We can't ignore the importance of renewables. They are here to stay. They are here to help us. All right? Carbon neutrality, zero carbon, they are all related. But of course, there are certain things that we have to pay our attention on, and that is to see whether we can scale up ACC, which is the fourth point over here. And then finally, my point about going for ultra-high biochar contents. And in fact, you can take away the biochar and put in something which is bio-related. All right, there is a pathway, and I think, well, this is something that we should all work on together. I'd like to thank NRF, MOE for all their support. And these are two of the newest journals that thankfully I'm part of. And if any one of you is interested to know anything about them, come talk to me as well. And this is my contact. With this, I'd like to thank all of you for your attention.
Fascinating. Right, getting down to materiality and almost at the kind of molecular level to look at, to really push the boundary of the possibility. I think research, as you can see, remains a critical component to advance all the stuff that we've been talking about. However, so often the gap between research and application in our industry is just so long. We would like to expedite that and push that along much, much faster. I hope that will be a goal moving forward. And certainly here in Singapore, I think the government and the agencies' vision is very consistent to really provide that kind of support and incentives and resources to drive this very quickly because of the existential challenges that Singapore particularly face. So let's all be part of that. So now, last but not least, final speaker for our session, Dr. Rizal, please come forward. I'm really glad to have him. He's no stranger to us, to Singapore. He's really an engineer, a design visionary. I think the key word here, as has been underlying a lot of the work, is about design thinking, creativity, and an educator. He's the global design director of Rumble and the founding director of Web Structures and Web Earth. Has been working with us and with NUS, for that matter, on many projects. So his latest initiative is on advanced computational design, which happens to be my PhD topic as well, aims to redefine the collaborative nature of designers, working with machines to overcome those complex compound challenges faced by building industry and the environment, where we need to deploy all this great and exciting stuff. So Dr. Reza, over to you.
Thank you very much. We've overshot the time, so I'll try and do it as quickly as possible. When I first was invited to speak here, having seen the list of illustrious speakers whom you've seen so far, I was pretty sure that the core topic of today, carbon and conservation, would be more than adequately and beautifully covered, and I was right. So I decided not to talk about carbon so much, but talk about the systems in which carbon, is a component, and how within that system the whole issue of carbon can be handled. So I structured the talk along sort of 5 or 6 sections, each a few minutes. A prelude, an introduction to system thinking, if you like, for a couple of minutes. The context of carbon in the environment, a little bit about carbon, the tunnel vision, and then talking about optimizers and disruptors, what paradigm shifts we need that a lot of other speakers have spoken, and then I want to finish with a book recommendation. So see how much of it I can get before I run out of energy. It's my lunchtime. In the way of a prelude, I wanted us to remember William Lim. A lot of us know him. A lot of us have come in contact with him. a stalwart of architecture, of design, of thought in Singapore, something that we don't have as much time to do about. We want to do things and get things done. And he was one. And we lost him a few weeks ago, just Chinese New Year, and it's the first time I'm having a public speaking role since he passed away, and I thought I wanted to use my time to remember him. He touched my lives very, very positively in contacts that I had with him, and I'm sure a lot of people would share that sentiment. Now, natural systems. A little bit of a system, system thinking is something that has been around for about 100 years, since the 1920s, etc. In the past, more recent 50 years or so, people like Donella Meadows, Fritjof Capra, and other people, Jeremy Lent and others. We've got a couple of system thinkers in the audience here, systems teachers as well. But I use the example given by the late Professor Akoff, systems teacher, his definition of it. And he says the system is a whole, and he insists the whole with a W. System is a whole comprising two or more components working together interactively to produce an outcome, a product or a service, that none of the parts or any subsettings of them could produce on their own. So it's about parts and about interactions. The system is a whole comprising two or more components working together interactively to produce an outcome, a product or a service that none of the parts or any subsettings of them could produce on their own. The human body is a biological system comprising these body parts. None of the body parts could do anything until they're connected to one another. That is a sort of basic definition of systems. So when we say a whole is more than a total sum of its components, its parts, what is more is the interactions that most of us find it difficult to see because it is not a physical thing. So that is why system thinking is important. We need to learn to see the connections and interactions. Now, why do we need systems? Because life is complicated, as we've heard, or is it complex, or chaotic, or disorderly? A simple context where we're dealing with known knowns, where pre-existing solutions exist to every problem that we have. So the job of a leader or a designer is to find a solution which already pre-exists, and boom, you're done. Next level of context and complexity is things which are complicated, where we are dealing with known unknowns. In this context, also, pre-existing solutions always exist, except that there isn't one answer. There are two or three solutions which are correct. So that our job is, as designers, to find the right one. And again, Bob's our uncle. The next level is complex, where we're dealing with unknown unknowns. In this level, right answers do not exist. We must always construct solutions and answers. Higher than that is chaotic, when we're dealing with unknowables, and the one after that is disorderly, which is a mixture of all of these guys. Issues to do with the environment and carbon are always either complex, chaotic, or disorderly. There is no simple solutions for it. So anybody who comes up with a simple solution to an environmental problem, you can bet is a wrong answer. As they say, every complex problem has a simple solution, which is wrong. So when we deal with carbon and the environment, I think we need to appreciate that we are in those areas. No simple answers exist. So anybody who offers that to you is either misleading himself, herself, or you inadvertently, of course. Now, how do we improve a system? By improving parts as well as the interconnections and as well as the relations. Again, a quote by Professor Akoff. If we have a system of improvement that is directed at improving performance of the parts taken separately, you can be absolutely sure the performance of the whole will not be improved. So if you have a whole where you're looking at carbon, Within carbon, you're looking at concrete. Within concrete, you're looking at whatever. And improve those things. Taken outside the system, you can bet your life that the whole system will not be improved. And that is the struggle that we've all had for the past 50, 60 years at least, where the carbon curve continuously goes up with all these beautiful work, some of which we've heard today, and millions of other people like us who are working on these things. Still, the challenge is getting bigger and bigger. It's not getting smaller. So system thinking is a good way, a good start for us as architects, as engineers. So if this guy, a system, if you take it apart, it's a dead man. To improve his arm, you should put it together and always look within the system to improve its parts, his arms or whatever. If you take his arms out, he's a one-armed person. Now, going from that, now what is the context? In the context of our environmental challenges, the core topic of today, we've identified within the company 16 drivers which form a system, the environmental system, that we ought to tackle. The drivers, water. Of course, water is a major issue, and I don't have time to go through the details of it, and you all know that. We don't have enough fresh water. We don't know how to drain water. We don't know how to harvest it, despite all the beautiful work that a lot of people do. Vegetation is an issue, not sort of manicured landscape, but rewilding. It's a concept. It's one of the drivers within the environmental system. Biodiversity is an issue. We all know that. Since 1970, we have lost 70% of the biodiversity that existed in 1970. It's a huge problem, part of the things. Air is a driver, of course. Carbon is an issue which has been going up. But so are 12 other items. Collaboration is an issue. Sound is an environmental problem. Voids, justice, environmental justice, and everything else, including economy, the way we value our work and our things, as well as politics, the way we govern ourselves. So you want to deal with carbon, which is inside the air. You need to look at that in the context of this whole system. If you take it out and deal with it, I think it won't get us where we ought to be going. What else do I have here? So the way we deal with it on a project or a brief, for every project or a brief or a site, we list out these drivers, and we see what are the opportunities that exist for the site or the brief to improve on these drivers on the site, not to be less bad, but to be more good, to be better, to do better than what existed. And we rate it from 1 to 10, 10 being very good, and have a chart like this and compare it with a standard, sustainable approach, sustainable paradigm. We've been talking about paradigm change. And then see how the improvements can potentially happen. And we apply it to projects. This is one, sort of we applied it to a mega tall, 500 meters tall project and compared it with the standard ones. So these are the sort of efforts that we're making to bring all of these parameters together. And of course, we are looking at 16, there are hundreds, and the whole planet is one living system that we all say that. It's not a cliche, it is. This is like a year in the life of the planet, how it is breathing, going and living for 1 year. What else? Now, looking at the tunnel vision, if you like, of carbon, I want to share a couple of projects and how we've sort of, is that one? No. You're familiar with the numbers, the graph, the CO2 equivalent parts per million going up. Since the industrial revolution, about 1790s, the amount of carbon was 278 parts per million. In 1984, around Brundtland, it was 345. Now it hovers around 420 or something parts per million. In the past 35 years since Brundtland and all the beautiful efforts on sustainability, we have increased as much, if not a little bit more, than the preceding 200 years. Despite all these beautiful efforts, where are we going wrong? What is the problem? Why can't we bend the curve? Because if this is the total carbon emission, greenhouse gas emissions, CO2 equivalent, currently hovering around 40 to 50 gigatons, depending on what we measure. There are paths ahead of us. One is the path of the deniers. We have no problem, we don't need to do anything, we just carry on as we are. We go into 4.1 to 4.8 degrees temperature increase compared to 200 years ago. And there is a path of optimizers, the sustainable route being less bad, going to 2.9 degrees, both of which are devastating. Along those paths, if we can continue, the construction waste in 2025 is going to be 1.1 billion tons. We can continue to demolish buildings as we do, which have the same environmental impact as setting fire to forests. The amount of chemicals in the next 10 years are going to be doubling in the world, and that really baffles me. The projection is, and more than 30% of these chemicals are harmful chemicals. This is the current path of either sustainable or the denier's path. The other path needs to bend the curve. The path towards 1.5 degrees is a major disruption. Almost none of the things that we've done so far, we're doing, has responded to that. We need to change that paradigm beyond cliches and beyond talking about it. And that one is the path of regeneration. Again, we have regenerative thinkers and designers amongst us and teachers amongst us. And on that path, the natural environment with beautiful colors, symphony of shapes and form, very rich in shape, in forms, but very frugal in choice in use of materials. In contrast, the built-up environment, everything is 90 degrees, everything is square, everything whatever, very, very poor in shape and form, or very wasteful in materials. So a regenerative environment is one that combines these two, and we still build as we need to build, but we underpin our buildings with the wisdom and the systems that exist in nature. So we need to learn from our biologists. We need to in the whole overall system, we need to talk to people from outside our industry who understand nature better than we do. In the paradigm shift, cultural change, language must change. We're talking about a different lexicon. The lexicon of sustainable is about conventional materials, it's about fossil fuel, it's about traditional design methods, etc., etc. It is about a monospecies interest, people-centric, human centricity, etc. And at best, it sort of optimizes, makes us a little bit less bad. The lexicon of regeneration is different. It's about new materials and composites. It is about renewable energy, augmented design methods, etc. Quite different sort of set of words, concepts. Interests of the unborn, the future generations, must be considered in our design. And that is the path to 1.5 degrees. Now, with this sort of long introduction, let's talk about a little bit about optimizers and disruptors. We're all optimizers. I see myself as an optimizer, despite all the efforts and all the commitments that I would like to think I have to a safe environment for the future. And I share with you a couple of our projects and how we've dealt with it. This is the new. This is the new Science Center, a competition winning scheme with Zaha Hadid's office. Is organized around what we call bars, these long elements of real estate. 5 bars, 1, 2, 3, 4, 5 bars, which are oriented to deal with the brief and to create the real estate that we want. Just to give you a sense of scale, this dimension from here to here is 100 meters clear span, which is because there's a view corridor there and there's no structure should be had there. So the way we did it through topology optimization, advanced computational techniques, we developed the structural frame as if it would grow from the ground. If this building was designed and built by nature, the structural frame would look like this. It's the skeleton that you have. The white areas are where the higher forces exist. You need more material. The darker the areas, less stress and less material is required. So the beauty of it is that when you look at this cantilevered portion, for instance, when you look at this cantilevered portion, see the stress pattern on the structure. It resembles the beautiful stress pattern or the structure of the cantilevered wing of this dragonfly. With these techniques and this, we're getting closer to the mind of nature. We're getting to know the frugality of nature, how that we can emulate at least. This is the model of a single column. A straight column can be modeled like this. From a single column to the most sophisticated tree structure is modeled in this one element. Down here, there are 5 or 6 nodes. If we call this 6 equal to 1, this becomes one column. Or it can become as complicated as we need it to be. We then take it through a geometric optimization. And you end up with shapes which are more prevalent in nature. We need, if we want to get different results, our buildings need to start looking different. If at the end of the day, our buildings look the same as they did 100 years ago, 80 years ago, 60 years ago, look and aesthetic is not the key thing, but of course, it matters. If our buildings look very poor in shape and form, then we are being just as wasteful. So with these things, you get buildings which are structures which are more of the sort of thing that you see in nature. But to make it, I need your help, a click here. But to make it buildable with those complexities, can I have yeah. We see how can we make this complicated structure with one element size. So we simplify it by all of these being made out of one single size. And it is possible. So you can have a frugality of material, but richness of shape and form. And of course, you could 3D print or and other methods that we all need to work on a bit more. And this is a tree structure project we sort of developed with Warha guys. That is for new buildings. For existing buildings, of course, there was a lot of talk about retention and how beneficial that is. We've done a lot of good efforts on Pear Bank. We put a lot of efforts, a gallant effort, I've called it, to retain it and did detailed studies to show how vast majority of the existing structure could have been retained while the new GFAs could be added, et cetera, et cetera. We failed there, but our collective efforts, the whole industry's effort, yielded good results on this one that we heard earlier on, which is now retained. A couple of, I think in my last couple of slides, but this is a standard, up and down project, 40-something stories. We did about 15 years ago, Grand Hyatt in KL. At that time, the embodied carbon footprint of a project of a structure of that nature would be around 500 kilogram per square meters. Through these optimization methods of 15 years ago, and we are a little bit better now, we've reduced that to 300. And that was about 20,000 tons of CO2 equivalent reduction. Now, reducing 20,000 tons is equivalent to the carbon that is sequestered by 8.7 million trees, which is the whole of the Singapore nature reserves, and or equivalent of taking something like 685 cars off the road for a year. So these are optimization methods. These are good. Now, I would say, is this good? I would say yes, but is this good enough? No, it's not good enough because the CO2 that we are all emitting into the atmosphere is continuously going up, and is going up in a straight line, as if nobody has done anything to bend this curve. It's just as a straight line. Now, this is the one for the energy sector, about 36 or so gigatons, which is about 80% to 90% of the total greenhouse gas emissions into the atmosphere. The point I'm making here now is that the vast majority of our carbon footprint is our energy footprint, which is in the energy sector, in fact. So unless we decarbonize the energy sector, all the beautiful work that we do stays within the realms of optimization. 10% reduction, 20% reduction, 30% reduction. They're good, but they're not good enough. So the disruption in our industry in terms of carbon is not going to come from within our industry, it's going to come from the energy people. And we need to help them if we can, in whatever way we can. In 2020, the total CO2 emissions for the energy sector was 34 gigatons, depending on with this sort of division of industries. They are aiming to reduce by 2013 by about 18% to 28.5, and they are aiming to reduce it by 2050 by a whopping 78%. By 2050, even if we build our buildings exactly as we're building now, which of course we're not going to do that, we're going to do better, the carbon footprint of our buildings is going to go down by 70%. So that is where the real thing exists. So we need to, in a systemic way, we need to work with biologists to understand nature, and we need to work with energy people for the sort of efforts that they do. My last slide, talking about systems, a beautiful book by Fritjof Capra, Patterns of Connection, where he's collected a set of essays that he's written in the past 50 years. And it is beautiful to see how in the 60s and 70s and 80s, these guys were talking about ecology. And he's a quantum physics person turned Eastern mystic person. So moved across the whole spectrum and sees the whole thing as one system. Thank you.
Thank you very much. Great. Again, thank you for hanging in there. I know some of you are probably really, really hungry, but we'll spend maybe 10 minutes for any questions that you would like to direct to the panel of speakers, okay?
I'm just curious that they say that cities like Paris, Barcelona, with a low height hit very high densities. They are a lot more pleasant to walk with from a human scale perspective also. And we know that timber construction, someone said in the last time, is easily gets to 6, 7 stories. There have been past examples in Yemen where just using mud, you have built skyscrapers to 5, 6 stories. Bamboo is a big thing. So what prevents us, as you had mentioned, that till you change the materials that we use, so what prevents us? We know everything. I mean, the last presentation, we know there is a monster looking us in our face. So what prevents us then to just say that we are going to use these materials? Of course, context is predominant, but I'm just curious that why don't we build low and why don't we build things which does not use any cement and steel?
We're all getting desperately hypoglycemic, so very low sugar level in the brain. That's why I was hoping Wolfgang would answer this. That's the million-dollar question, isn't it? I mean, it's a good question, and you know, if you talk to a lot of urbanists around the world, and I've had conversations with Rahul Mehrotra, Ashok Lal in India, who talk about Indian cities. They all advocate rise high-density developments. They advocate polycentric human settlements, where instead of building these mega cities with tall buildings, we have smaller agglomerations of cities connected by high-speed infrastructure. But I think to the point that was raised this morning, the problem is not the solution, it's the culture, it's the way we think about the problem, the questions that we ask. India, for example, is investing a ton of money into smart cities, but how can you be smart when there is no infrastructure? You know, what does smart mean in the absence of infrastructure? So I don't mean to make a specific example of that. I'm just saying that if you don't ask the right question, then you're bound to get stuck in a loop, you know, in doing the same thing over and over again. I don't actually have an answer, specific answer to your question, but I think a lot of it is mindsets, policy, governance, you know. This is where it comes from. I think you were saying that it's the energy sector. You know, we did a modeling, by the way, for our carbon calculator where we said, oh, and what if Singapore were to change from natural gas to hydrogen? You know, what would that? Everything dips down. You know, we can call it a day. We don't have to do that much. You know.
I think it is important. I'm not sure whether you were asking a question or you gave an answer. We're saying that Paris is a solution to all our sort of cities. You see, there is. No, I was just kidding with you. What I'm saying is that if low-rise and dense building, urbanism, is the answer to all our problems that we have, I would say that's too simple an answer. That's probably not the right answer. It's definitely not global. That's a good answer to Paris, but maybe I'm an advocate of high-rise and mega tall, because that is where you get densities of 200,000 people, not 8,000, 10,000, 15,000. If you can make that livable environment, that is a challenge for us. Then we've got the density issue resolved as well. But that is the thing. I think that part of the thing about regeneration, and you say that in your talks as well, is about humility. That we need to accept that the carbon problems in our built environment cannot be solved by us. It doesn't matter how great we are as architects, as material scientists, as structural engineers, as etc. We can optimize, we can make things better. But we need to see ourselves as part of that whole system with the energy guys, and that is where the problem can be solved.
Should I add a problem? I'm a little bit reluctant to wish that we could delegate the solution to somebody else. It sounds easy to delegate and to think about that if we decarbonize our energy sector, everything is solved. Yes, it's true. If we decarbonize. But how do we do that? Let's go back to Singapore. You run on natural gas, basically, all your electric power, which gives you the 400 and something gram per kilowatt hour. If you want to change that to hydrogen, how do you do that? How would Singapore do that without being part of a system on this planet? So without being connected to the world all around? I always say, then you need to borrow energy from somebody else or resources from somebody else. This is not a solution, what I'm saying. I'm just a kind of shy to come up with these ideas that somebody else is solving the problem for me. I don't want that my children need to say, hey, Dad, you knew it at that time. So what was your contribution? And this gives a kind of shyness, see? Yeah. And let me turn it around. We need to do more by ourselves. That is totally not the question you brought up. But coming to your point, the world is so different and so diverse that the answers are different and diverse. And me coming from a city of low-rise, you already hear where my view and where my direction would go for a lively and lively full city, which I would seek more in that context of a European city. But the world is too diverse to get one single answer to this. Not the numbers will tell us.
Quick answer on the materials. I'm not going to refer to any materials in particular, but I think in general, in order for a new material to be adopted or even diffused within an industry, it can be construction industry, it can be something else, the cost must be correct. And in order to drive the cost down, there must be economy of scale, enough people to want it, enough people to produce it. But in order for people to produce it, the code, the guidelines, the standards must be in place. And I think in many of these cases, there isn't any ready-made industry standard that can be readily adopted by the industry in order to very quickly put these new materials into the market. And that is always lagging behind the innovation in technology and in science. One of the many reasons.
Thank you. By the way, you didn't mention his name. This is Mr. Mavendra. He's been doing work in Rajasthan, looking at regenerative design in a massive scale. So look forward to working with him moving forward. Okay, question. Yes.
I'm Sheen, and I'm a student at the Building Performance and Sustainability program here at NUS. And I was wondering, the latest buzzword or the latest talk of the town is a circular economy, and we are aiming for completely independent buildings. Yes, we talked a lot about energy-wise, but can buildings really be independent in all of their systems? And how far or near are we to that goal? What do you guys think?
Yeah, we studied circularity in ISD a couple of semesters ago, looking at a master plan for the north of Singapore, an industrial estate. And one of the conclusions was that circularity is a multi-scalar problem. It cannot be solved at the scale of the building. There is so much you can do at the scale of the building, at which point the neighborhood scale must kick in. There must be things that happen at the scale of the neighborhood. And even that has its limits, and then you go on to the regional scale, and then the island scale, the metropolitan scale. So I think it's a misnomer to think about circularity as a building problem. It really is the ecosystem of business and material flows at the scale of the city, if not wider. So it is a system of systems problem. You know, every scale of that system has to act to participate in that circular flow, but the problem won't be solved at one scale.
Hi, this is Ruchi here. I'm part of the ISD program, and I'm a practicing urban designer and sustainability consultant as well. I just had a question, and it struck me when I was looking at the different structures that Dr. Rizai was presenting, and I was thinking that in the pursuit of using sustainable materials or materials that are less carbon intensive, are we creating structures that use more material eventually? Could be greener material or could be, but we are using more, I felt, instead of, for example, the tree structure, a single, like the minimalistic designs we used to talk about, less is more, and pure functional structures versus the structures that use more material. So it's a debate, but what are your thoughts? Because you guys are dealing with numbers, so what does it come to?
Sure. There's a beautiful book by Michael Pollan, Biomimicry in Architecture. There he's got like 5 or 6 columns, structural columns, showing one is a solid column, a simple one. What is the use of material? 100%. And the next one, some voids created into it, carrying the same load, 82%. Material. More voids. The more you complicate the shape, the less the material becomes. So while in that complex things, the most complex of the shapes would have the lowest amount of material in them. So one single column would be much bigger per se. So definitely it always follows, definitely from a structural thing that I can say, that always more complex shapes, less materials. You don't agree?
No, I'm not.
And then there's this strange thing that if you think that you want to store carbon by using a CLT or glulam or biogenic material like wood in your building, more is better. Strangely, but it's better, let me say, for a few years, for the period, as long as you could retain the building which is built out of wood. It's a strange thing, but it's a strong discussion what we have in Europe, you probably know that buildings made of more wood would store more. So less efficiency actually is better. Strange. It's related to what kind of material choice you make. But there is a second point which I mentioned before, which is like, are we really knowing that the 100% is the right choice? Or is the design sometimes giving us more options to reduce materials because it's quicker and faster designed like that? If you add 10 centimeters or whatever, probably. And if you put more smartness here, you can reduce material on the first choice and achieve the same, which I think is a huge, gives a door into a field where some opportunities could lie. Let me be shy here.
Hello, my name is Zahra. I'm also part of ISD program. I have a follow-up question about the biogenic materials. So in one of the slides, it shows that the materials have a negative value of carbon at the beginning, and during the construction, the value decreases. But it still stores the carbon and allows for carbon negativity. But from what I understand, please correct me if I'm wrong, the negative carbon comes from the carbon sinking of the organic material itself. So do we need to be concerned about this process of carbon removal from the natural ecosystem? And how different is the design approach as compared to use a conventional building in terms of life cycle carbon? Thank you.
I say a simple column is more material than a complex column and things like that. But these are obviously a little bit controversial, but factually correct. But there are other issues, as Nirmal mentioned. There are also like systems within systems within systems. Some of these complex homes we can't build. We don't have the ability to build. So it becomes simpler, easier, faster to build a material which is a column in which we have more waste, continue on our wasteful processes because time and technology issues, limitations that we have pushes us towards wasting material in our structures. So definitely, if I answer your question correctly, there are different materials are suitable or suited to different structural system in a structural case. Timber has its own limitation in terms of strength, in terms of stiffness, etc., long-term performance. So, I don't think there is one or the other material or one or the other system that is the right answer across everywhere, all projects. So, sometimes we have to use timber, we can use timber. Other times we use materials which are not as environmentally durable as timber, but they have strength and other things that we want, etc. So we need to have access to the whole range of materials and systems, and use our competence and judgment, etc., to make sure that we use the one that collectively gives us the desired outcome without breaking the environment bank, which is what we're currently doing. With all the numbers, we're doing that.
Thank you. A quick addition to that, and a short response as well. After all has been said about concrete and cement, are we going to see a future where we are not going to use concrete? Very unlikely. So it is here to stay, and I guess that in the future we'll begin to see more combination of concrete with other materials, biogenic materials, bamboo, wood, for example. What is more important is for all of us to bear in mind that when we design and construct new buildings, making use of the different kinds of material, including RC, reinforced concrete, and wood, we must leave behind a possibility for us to salvage all these waste and to reuse some of these waste in new buildings. Yeah, I think that is going to be relevant for many decades to come, rather than to say that, okay, from now on, I'm not going to use concrete. It's not going to happen. Yeah.
One last question.
Very quick one. So this is for Professor Kishnani. I'm a real estate development practitioner, but I'm also a part-time research student at Oxford University in the MSc of Sustainable Urban Development. I was wondering if you take exchange students.
For the master's program. Where's the head of department? He left. Well,
Program director.
at the moment, we don't have an exchange program, but come talk to me afterwards. We'll think about it.
Okay. All right. Well, thank you all very much. Great thank you to the panel speakers, earlier panel members, as well as this. And it leaves me also to thank the organizers and from the Senior Vice President's office, as well as Amy sitting there, and Patricia somewhere at the back, as well as the staff that have been helping to put all this together, symposium. I hope you have benefited from this. You know, I'm sure all of us go to all kinds of symposiums, meetings, and sometimes we come off really discouraged and don't know what to do, lost. Others say, wow, we're in the cloud, but how to do? So there are this whole range of challenges that have been, I hope that our speakers have given you sufficient, right, motivation and the methodology and the pathway in terms of changing mindsets, changing cultures, all the way down to the micro and nano material opportunities that are going to be out there. I hope that this symposium have given everybody bits and pieces of how you individually and collectively can engage in that whole ecosystem or life cycle. Now, I personally always have two very simple, simplistic way of looking at things, apart from pushing research. On the one hand, what we know can be done, must be done, should be done, we just must do it. It's not a question. Earlier, you heard the speaker say here in NUS, we've done a renovation. There is another 100 buildings like this on campus, which are not science buildings, not engineering buildings with lots of labs and equipment, just teaching spaces. We could now go out and do it and scale up all the lessons learned, both technically as well as the cost management. We now know how to manage that too. So it's just a question of doing it. And this is what they call, some people call low-hanging fruits. Always a caveat though, I learned about low-hanging fruits. And this is from William Ruckelshaus, who is the first Environmental Protection Agency administrator of the United States appointed by by Nixon. And then Reagan asked him to come back and do another term. I served with him on an energy foundation board, and we were all talking about low-hanging fruit. Where to go and look for the low-hanging fruits. And he, 80-year-old, extremely humble, smart, he was listening, and suddenly he said, guys, remember, not everything that is low-hanging is a fruit. That I never forget. Because sometimes we look at justification of those easy pathways. Cheap to do, so do, without the thinking through the consequence, right, of future sustainability. So, but there are other things that have been proven, can be done, must be done. The other is really about projecting future. Anticipating all these issues before, hopefully before they happen, and do research to solve it. We've done for decades now work on institutional buildings, commercial buildings. We know how to get to net zero now. Okay, just a question again, doing it. There are certain building types, and I'm glad JTC has taken on that challenge. The other building type that we need to pay very much attention to is the healthcare sector. Very little data. We don't even know where the electricity is going to all the machines very often. We need to tackle that, especially not just in Singapore, but in the region with the growing elderly population. And of course, for nations that are a bit more affluent, they want to have all kinds of tests and all kinds of treatment. All that also has consequence on carbon and energy. We need to preempt that and tackle that moving forward. So those are the kind of extremes that we can do something about moving forward. So with that, thank you again, everybody, for hanging in there. Remember, all of you are invited to the opening at 3:30. So please come if you can. Meanwhile, I'm hungry. I'm sure you are too. Thank you very, very much.